So in section 13.4, we're going to talk about the definite integral. We're going to look at that from an algebraic point of view, and we're also going to talk about one of the huge things in calculus, which is called the fundamental theorem of calculus. You will need to know all of this information in this section, as in any other section we've talked about. So remember, chapter 13 is talking about integration, finding the most general antiderivative, which is the same thing as saying evaluate the integral. We learned a technique of integration in sections 13.2 and 13.3 called U substitution. Now we're going to connect all of those ideas and techniques as well to that of the definite integral and the fundamental theorem of calculus. So what this section really does is it connects differential calculus to integral calculus. Let's start out with the fundamental theorem of calculus, which I will write as FTC. So let f be a continuous function defined on the closed interval AB, and let capital F be any antiderivative of your function little f defined on the closed interval AB. Then we can say the following. We can say that the integral evaluated from A to B of f of x dx is equal to capital F of B, which is your antiderivative evaluated at B, minus capital F of A. Okay? Moreover, an antiderivative of at little f is guaranteed to exist. Okay? So, in words, what this means, what this mathematical statement means here, or equation means, is that every continuous function has an antiderivative. And to compute the definite integral of f of x over the closed interval AB, then first find an antiderivative, capital F of x, of little f of x. Then evaluate it, being your antiderivative, at x equals b, evaluate it at x equals a, and subtract the two answers. If you need to listen to this again, rewind the video, but you will need to make sure you understand this concept. Note that it's STAR. This is the fundamental theorem of calculus. So let's look at some examples. In our first example, we are going to evaluate the integral. This case it happens to be definite. And we know it's definite because it has an upper limit of integration being 1 and a lower limit of integration being -2. Okay? So, anytime you see numbers at the ends of the integral symbol, then that implies you have a definite integral. So, let's go ahead and evaluate this using the fundamental theorem of calculus. So, this is equal to the antiderivative of x minus 2 is x squared over 2 minus 2x, right? Because when you take the derivative of this, you get the integrand x minus 2. Now, we need to evaluate that from -2 to 1. So, we found our antiderivative, and now we need to substitute in our values. Remember, you have to start out with substituting in b and subtract what you get when you substitute in -2. Okay? It does matter. You must use b first, substitute it in here, minus what you get when you substitute in -2. Okay? So, we get 1 squared divided by 2 minus 2 times 1 minus, so this is your f of b, minus -2 squared divided by 2 minus 2 times negative 2. Okay, so that's equal to 1/2 minus 2 minus negative 2 squared is 4 divided by 2 plus 4, and that gives us, whenever you simplify it, that gives us negative 15 halves. And that's your final answer. So we just evaluated a definite integral. That's called a definite integral. Okay? Now, let's evaluate the next example. Evaluate the definite integral. The integral from 2 to 3 of x plus 1 over x dx. Okay, so we find the antiderivative. That's equal to x squared over 2. Remember, the integral of 1 over x is the natural log of the absolute value of x. Make sure you're careful there. Okay, so that's the antiderivative, and we evaluate it from 2 to 3. So this would be equal to 3 squared. So we substitute in 3 first, divided by 2 plus the natural log of 3. Note that I got rid of the absolute values because the absolute value of 3 is 3. Minus, now we substitute in 2. So we have 2 squared over 2 plus the natural log of 2. So this gives us 9/2 plus the natural log of 3 minus the quantity 4 over 2, which is 2, plus the natural log of 2. Simplifying, you can write 2, let's erase this, as 4 over 2, so it'll make it easier for you to simplify. So that is equal to 9 over 2 minus 4 over 2. We're just doing some rearranging and distributing the negative, plus natural log of 3 minus natural log of 2. So we distributed the negative here, and we just rearranged the terms. So this gives us 5/2 plus the natural log of 3/2. And that's your final answer. If you're wondering where that natural log of 3/2 came from, then recall that the natural log of x minus the natural log of y is equal to the natural log of, that should just be big, of x over y. That's what we used. Okay? We have a few more examples. We're now going to look at those. So here, let's start. We need to find the antiderivative. We are evaluating the integral from 0 to 2 of e to the negative x plus 1 dx. Now, here you have to be careful, okay? So you have your antiderivative here is negative e to the negative x plus 1, okay? And we're going to evaluate that from 0 to 2, okay? So you might be wondering where that came from, so let's do an aside. If we take the derivative of this function, we need to make sure that we get our integrand back. So this is just a check to show you that this is indeed, this being negative e to the negative x plus 1, that is indeed your antiderivative. So here we have the derivative is negative e to the negative x plus 1 times the derivative of negative x plus 1. Remember, because you have to use the chain rule. So that's equal to negative e to the negative x plus 1 times negative 1. Well, you have a negative times a negative gives you a positive e to the negative x plus 1. And that is your antiderivative, so we are correct. Awesome. Notice that when you're dealing with the definite integral, you don't have to add a plus c because you're able to find an exact value. Okay? So this is equal to, now we substitute in 2 and we have negative e to the negative 2 plus 1. We have this minus negative e to the negative 0 plus 1. Well, that's just equal to negative e to the negative 1 minus, well, technically we're subtracting a negative, so that's plus e to the 1. So we can rewrite our answer as negative 1 over e plus e. There you go. All right, awesome. So let me just draw a line here to separate that. Now what we want to do is we want to evaluate the definite integral from 0 to square root of 2 of x times the square root of 2x squared plus 1 dx. What does this look like? This being this integrand. This integrand, notice that you have a composition of functions and you have an x out here. So based on your integration techniques, your alarm should be going off and light bulbs should be clicking and or lighting up. And you should notice that you're going to have to do u substitution. So let's do a u substitution. This problem is screaming for a u substitution. Okay, so we're going to let u be equal to 2x squared plus 1, and then du is equal to 4x dx. And we don't see a 4, but we do see an x dx there. So then we're going to divide both sides by 4 here, and we get 1/4 du is equal to x dx. Okay? Now, one thing when you do a u substitution for a definite integral, when you put your function, your integral, in terms of u, your limits of integration also need to change. So note that when x equals 0, u is equal to 2 times 0 squared plus 1, or in other words, it's 1. So we'll need to remember that. Then when x is equal to the square root of 2, u is equal to 2 times the square root of 2 squared plus 1, or in other words, it's equal to 2 times 2 plus 1, which is 5. We'll need to remember that as well. So using all of this information, our integral, so using all of our substitutions and stuff, we now have that our integral is equal to the integral. Notice that instead of 0, we're going to write 1. Okay? Instead of square root of 2, we're going to write 5. Because now we're switching to u. And this is going to be, notice that x dx here, we're going to substitute in 1/4 du And then you multiply that by the square root of u. Okay? So this is equal to, the 1/4 comes out, times the integral from 1 to 5 of u raised to the 1/2 du. That's equal to, remember now you need to find your antiderivative. You do that. We get 1/4 times 2/3 u to the 3/2 evaluated from 1 to 5. If you're questioning where that came from, take your steps. Take steps if you need to find the antiderivative. So remember u, the integral of u to the n du is equal to u to the n plus 1 divided by n plus 1 plus c. But because we're dealing with definite integrals, we don't need that c here. Okay? So, applying that to u to the 1/2, you will get 2/3 u to the 3/2. Okay? So, this is equal to 2/3 can come out, right? So you have 1/4 times 2/3 gives you 1/6, and then you would have u to the 3/2 evaluated from 1 to 5. We get 1/6 times 5 raised to the 3/2 minus 1 raised to the 3/2, which is just 1. And that's your final answer. Okay? Awesome. So now we have 2 more examples to do from this section. Part E says we want to evaluate the definite integral from 1 to 2 of the square root of the natural log of x divided by x dx. Well, this integrand looks somewhat complicated, and we know the numerator here, the square root of the natural log of x, that's the composition of functions. And we are dividing by x, so that implies that there may be a derivative somewhere in there. So that means that in order to undo that or find the antiderivative, we need to do a u substitution. So let's let u be equal to the natural log of x, and du is then 1 over x dx. Okay, is that hard for you to see? So let's do an aside over here and note that the square root of the natural log of x divided by x is the same thing as 1 over x times the square root of the natural log of x. So now what you may be able to see a little bit more is that if you rewrite your integrand like that, you'll have your 1 over x dx there. So we'll leave du as is, and then we're going to change our limits of integration as well. So when x is equal to 1, u is equal to the natural log of 1, or in other words 0. When x is equal to 2, u is equal to the natural log of 2. Now, using this substitution, our integral becomes the integral from 0 to the natural log of 2 of the square root of u du, right? So if we write the integral here and we put dx there, we have the integral here and dx here. So note that you have your 1 over x dx is the same thing as du. Okay? So that's your u substitution. And now we integrate. This is equal to the integral from 0 to the natural log of 2 of u to the 1/2 du, which is the same thing as whenever you find your antiderivative, remember, take the steps if you need to. It's going to be 2/3 u to the 3/2, evaluate it from 0 to the natural log of 2. And now we have that this is 2/3 times the natural log of 2 raised to the 3/2 minus 0. Well, that gives us 2/3 natural log of 2 raised to the 3/2. This is our final answer. Notice that with definite integrals, again, you don't have to add the c because you're actually substituting in your limits there. Okay? Now, there are other things that we can do with definite integrals. And this is going to lead, this next example is going to lead to what we're going to talk about more in section 14.2, which is the area between two curves. And we're going to look at applications of that. So, move this up a little bit so we can have more room. Let's calculate the total area of the region described. Do not count the area beneath the x-axis as negative. So we want to calculate the area of the region bounded by the line y equals 2x, the x-axis, and the lines x equals 1 and x equals 2. Move this up a little bit more. So let's sketch a graph here. So we want to graph y equals 2x. We have our x-axis. We have our y-axis. We want to graph y equals 2x. So when x is 1, y is 2 times 1, or in other words, 2. 4 and 6. When x is 2, y is equal to 2 times 2, or 4. When x is 3, we get y is 6. When x is 0, we get 0. So the line looks like so. So that's y equals 2x. Okay, we know that our curve is, or we know that this region said is bounded by the line y equals 2x, the x-axis. So let's switch our colors. The x-axis the lines x equals 1. X equals 1 is this vertical line here. And x equals 2, which is this vertical line here. Okay, so we want to find out what area this is. We want to find out what the black area is. Okay, so in order to do that, we know, again, that's x equals 1. This is x equals 2. So we know that mathematically, to find the area, that means we want to integrate. So we have that region, that black area, is equal to the integral from 1 to 2 of 2x dx. Okay, so this is equal to, the 2 comes out, and then we're integrating from 1 to 2 of x dx. We find the antiderivative. We get 2 times x squared over 2. Evaluate it from 1 to 2. Your 2's cancel. And so that gives you x squared. Evaluate it from 1 to 2. Or in other words, you get 2 squared minus 1 squared. Or in other words, you have 4 minus 1, which is 3. So this area that's bounded by the line y equals 2x, x equals 1, and x equals 2 is 3. That's equal to 3. That's your final answer. Okay, so that concludes the definite integral from the algebraic viewpoint and the fundamental theorem of calculus. Make sure you go through your homework problems.